Look up at the night sky, and what do you see? A scattering of stars, maybe a planet or two. But what if I told you there's an invisible architecture weaving it all together? A hidden scaffolding stretching across billions of light years, connecting galaxies in a delicate dance of gravity and mystery. This isn't science fiction, it's the cosmic web, the universe's grand design, and it holds secrets that defy everything we thought we knew about space. Think of the cosmic web as nature's ultimate masterpiece, a tapestry of dark matter and galaxies arranged in patterns so precise they seem almost intentional. Some formations mirror fractals, repeating their intricate shapes at every scale. Others twist into vast, swirling filaments, like rivers of starlight flowing through the void. And then there are the voids themselves, enormous, empty regions where galaxies refuse to gather, as if the universe carved out pockets of silence in its symphony of matter. How does this hidden order emerge from chaos? What invisible hand sculpts these patterns? And what do they tell us about the forces shaping reality itself? That's exactly what we're about to explore. In this journey, we'll uncover 22 of the most astonishing patterns woven into the cosmic web, each one a clue to the universe's deepest mysteries. From the eerie alignment of galaxies to the gravitational echoes of dark matter, these aren't just curiosities, they're windows into the laws that govern everything. By the time we're done, you won't just see the night sky differently, you'll feel it. Because once you glimpse the hidden order behind the cosmos, there's no going back. So let's begin. The cosmic web isn't just a random scattering of galaxies, it's the universe's architectural blueprint, written in gravity and dark matter. Picture the largest spiderweb imaginable, stretching further than our most powerful telescopes can see, with galaxies clustered like dewdrops along its silken strands. What's astonishing is how this vast structure mirrors patterns we see in nature on Earth. The branching veins of a leaf, the intricate neural networks in our brains, even the way rivers carve their paths across continents, all echo the cosmic web's elegant design. This isn't coincidence, it's a fundamental pattern woven into the fabric of reality itself, appearing at scales from microscopic to universal. Gravity acts as the universe's master sculptor here. After the Big Bang, tiny fluctuations in matter areas where particles were just slightly denser began pulling everything toward them over billions of years. Like cosmic magnets, these regions drew in gas, dust, and dark matter, forming immense filaments that galaxies would later line up along. Meanwhile, dark energy works as the counterbalance, pushing empty regions apart to create those mysterious voids where galaxies seem to avoid gathering. Together, these forces stretch the universe into this intricate web we observe today. Modern telescopes and supercomputer simulations let us peel back the curtain on this hidden architecture. The Hubble Space Telescope has captured stunning images of galaxy clusters strung along filaments like pearls on a necklace. Meanwhile, projects like the Sloan Digital Sky Survey map millions of galaxies, revealing how they trace out this vast network in 3 dimensions. What's truly mind-bending? The patterns we see match theoretical models, almost perfectly proving that the laws of physics paint this grand design with mathematical precision. Yet for all we've decoded, the cosmic web still holds mysteries. Why do some filaments glow with faint, unexplained radiation? What invisible threads of dark matter truly bind it all together? Each discovery pulls us deeper into the universe's hidden blueprint. If you could shrink the universe down to the size of a city, those galactic filaments would be its grand boulevards, sweeping avenues where stars and galaxies naturally gather, drawn together by the irresistible pull of gravity. Picture standing at a crossroads where these cosmic highways intersect, watching galaxies glide past each other in slow motion, some drawn into tight clusters while others continue their endless journey along the filament spine. The Sloan Digital Sky Survey didn't just map these structures, it revealed something astonishing. These filaments aren't random. They follow precise mathematical patterns, with galaxies spaced at intervals that mirror the harmonics of a musical scale. It's as if the universe composed a symphony, and gravity is the conductor ensuring every note lands in perfect time. What's even more remarkable is how these filaments act like celestial rivers, channeling the raw materials of creation. Along their lengths, clouds of hydrogen gas collide and compress, sparking the birth of new stars. This explains why galaxies along filaments tend to be brighter and more active than those drifting in the emptier voids between them. Imagine these filaments as fertile valleys in an otherwise barren cosmic landscape, where the conditions are just right for galactic life to flourish. But here's the twist: dark matter is the unseen architect behind it all. Though invisible to our telescopes, its gravitational fingerprint is everywhere, weaving this intricate network like a spider spinning silk in the dark. Computer simulations show that without dark matter's scaffolding, the universe would look entirely different. Galaxies wouldn't align into these elegant threads, they'd scatter like dust in the wind. That's the real magic of this pattern. It's proof that the cosmos operates by hidden rules, written in a language of gravity and shadow. And as we decode more of these filaments, we're not just mapping the universe's structure, we're reading its history, one luminous thread at a time. Now imagine stepping into one of the universe's most mysterious spaces, not a glittering galaxy or a swirling nebula, but a cosmic void. These are the empty rooms of the cosmos, vast regions so staggeringly large they could swallow thousands of Milky Ways without a trace. If filaments are the universe's bustling highways, voids are its deserts, silent, expansive, and almost completely devoid of matter. Some stretch over hundreds of millions of light years, their emptiness so profound that if you stood in the center, the nearest galaxy would be too faint to see with the naked eye. But don't let their hollowness fool you. Voids aren't just passive gaps, they're active sculptors of the cosmic web. Like invisible hands, they push galaxies toward the filaments, herding them into the vibrant clusters we observe. This happens because the universe is expanding faster in these empty regions, driven by dark energy's relentless push. Picture a balloon inflating unevenly. The emptier stretches grow faster, while matter-rich areas resist the stretch, creating tension that shapes the web's structure. What's truly fascinating is how voids act as cosmic laboratories. Their emptiness makes them ideal for studying dark energy's influence on the universe's expansion. By measuring how light bends around voids or how galaxies at their edges behave, astronomers can trace dark energy's fingerprints. Some voids even emit faint, unexplained radio signals, ghostly whispers that might reveal hidden physics. And then there's the eerie beauty of their silence. While filaments buzz with star formation and galactic collisions, voids are the universe's quiet corners where time seems to stretch thin. Yet even here, in the stillness, there's a story. The way voids grow and evolve could hold clues to the cosmos' ultimate fate, whether it will expand forever into cold emptiness or collapse back in on itself. So the next time you look up at the night sky, remember, the darkness between the stars isn't just empty space. It's part of the universe's grand design, a silent player in the cosmic dance. Somewhere in the darkness behind our own Milky Way, an invisible force is pulling thousands of galaxies off course like a cosmic magnet hidden behind a curtain of dust. Meet the Great Attractor, one of the universe's most puzzling gravitational mysteries. This region packs so much mass that it bends the paths of entire galaxies, including our own, which is racing toward it at over 600 kilometers per second. Yet for decades, astronomers couldn't even see what was causing this immense pull. The Milky Way's dusty disk blocked our view, leaving scientists to wonder, what lurking giant could warp space so dramatically? X-ray telescopes finally pierced the veil, revealing a sprawling supercluster of galaxies, a dense knot in the cosmic web where gravity's grip is extraordinary. But here's the twist: the Great Attractor isn't the end of the story. Beyond it lies something even larger, the Shapley supercluster, a behemoth containing tens of thousands of galaxies. Together, they form a gravitational cascade, with Shapley pulling the Great Attractor, which in turn pulls us. It's like a cosmic game of tug-of-war, where we're caught in the middle of invisible strings woven by dark matter. What makes this pattern so fascinating isn't just the scale of these structures, but what they reveal about the universe's restlessness. The cosmic web isn't static. It's a living, shifting network where galaxies flow along rivers of gravity. And the Great Attractor is proof that even with all our technology, we're still mapping the shadows of forces we don't fully understand. Could there be even larger attractors waiting to be discovered? Or does this gravitational puzzle hint at something stranger, a flaw in our understanding of physics itself? Every galaxy caught in this flow carries a clue, and as we trace their paths, we're not just charting space, we're decoding the hidden currents that shape everything. Dark matter is the universe's silent architect, the invisible hand shaping every strand of the cosmic web. Though we can't see it, touch it, or even directly detect it, its gravitational pull is undeniable, like a puppeteer guiding galaxies into place with unseen strings. Imagine building a skyscraper, but the steel framework vanishes once construction is complete. That's dark matter, the hidden scaffolding holding everything together, accounting for 85% of the universe's mass, yet leaving no trace beyond its gravitational fingerprint. The proof is in the patterns. Supercomputer simulations, like the groundbreaking Millennium Run, reveal how dark matter's tendrils stretch across the cosmos, forming a delicate lattice where galaxies cluster like fireflies on a spider's web. Without it, the universe would look utterly different. Galaxies wouldn't align into those elegant filaments or gather into shimmering clusters. They'd drift apart, unmoored and scattered, like leaves lost in the wind. But here's the puzzle. What is dark matter? For decades, scientists have chased answers. Some theories suggest it's made of exotic particles, slow-moving and ghostly, passing through ordinary matter like a shadow through a wall. Others propose we've got gravity all wrong, that Einstein's equations need rewriting to explain the universe's structure without invoking invisible mass. Then there are the wilder ideas. Could dark matter be primordial black holes, remnants of the Big Bang lurking unseen, or something even stranger, a substance that defies our current physics entirely? Every clue we uncover only deepens the mystery. When galaxies rotate, their outer stars move too fast for the visible matter to hold them in place, as if gripped by an unseen force. When light bends around galaxy clusters, it's not just the stars warping space, it's the hidden weight of dark matter, twisting reality like a lens. Even the cosmic web's grand design points to something missing, a shadow framework we've yet to fully map. The hunt for dark matter isn't just about solving a cosmic riddle, it's about rewriting our understanding of reality itself. Underground labs search for elusive particles in vats of liquid xenon. Telescopes scan the skies for distorted light that might trace dark matter's contours. And with every new discovery, we peel back another layer of the universe's hidden blueprint. One thing's certain, until we unravel this mystery, we're only seeing half the picture. The cosmic web's beauty isn't just in the galaxies we observe, it's in the invisible threads weaving them together, a tapestry stitched from shadows. Hidden within the cosmic web's vast tapestry are ghostly ripples, echoes of the universe's first cry. These are Baryon acoustic oscillations, frozen relics of sound waves that surged through the newborn cosmos just moments after the Big Bang. Picture the early universe as a scorching, dense soup of particles, where gravity and radiation waged a tug of war. Regions of slightly higher density pulled matter inward, while radiation pressure pushed it outward, creating rhythmic pulses, cosmic sound waves that rippled across space like the rings from a pebble dropped in a pond. But here's the astonishing part. When the universe cooled enough for atoms to form, these waves froze in place, imprinting their pattern into the distribution of matter. Fast forward billions of years, and galaxies still cling to those ancient ripple crests, clustering at predictable intervals like beads on a string. This delicate spacing, roughly 500 million light-years apart, acts as a cosmic ruler, allowing astronomers to measure the universe's expansion with breathtaking precision. Projects like the Dark Energy Spectroscopic Instrument, or DESI, are mapping millions of galaxies to trace these oscillations. By comparing the spacing of baryons at different cosmic epochs, scientists can track how dark energy has stretched the fabric of space over time. It's like listening to a cosmic heartbeat, each oscillation a pulse revealing the universe's rhythm of growth. What's truly humbling is that these patterns are a direct line to the universe's infancy. The same sound waves that once reverberated through a plasma-filled cosmos now whisper to us across billions of years, encoded in the positions of galaxies. They tell a story of how structure emerged from chaos, how tiny quantum fluctuations ballooned into the vast web we see today. And as we decode these ripples, we're not just measuring space, we're hearing the echo of creation itself, a fingerprint of the moment everything began. At the crossroads of the cosmic web's filaments, galaxies don't just drift, they converge into glittering metropolises, the universe's most massive structures. These are galaxy clusters where gravity's pull is so powerful it binds thousands of galaxies together in a single, swirling dance. Take the Coma cluster, for example, a sprawling city of stars over 300 million light-years across, where every pinprick of light isn't a star but an entire galaxy, each with billions of its own suns. Or the Perseus cluster, where superheated gas glows so intensely in X-rays that it outshines all the galaxies combined. These clusters aren't just cosmic landmarks, they're laboratories for testing the universe's deepest laws. What holds these colossal gatherings together? The answer lies in the interplay of forces we're still unraveling. The galaxies themselves are just the visible tip of the iceberg. Between them swirls a sea of gas hotter than the sun's core, so energetic it emits X-rays that satellites like Chandra can detect from Earth. And beneath it all, hidden from view, dark matter weaves an invisible net, its gravitational grip keeping everything from flying apart. Without this shadowy scaffold, these clusters would dissolve into chaos, their galaxies scattering like marbles dropped on a tile floor. But the real drama happens when clusters collide. Picture two cosmic cities smashing together at millions of kilometers per hour, a slow-motion crash that unfolds over hundreds of millions of years. When the bullet cluster famously rammed into another cluster, the collision ripped apart ordinary matter, leaving the hot gas trailing behind like smoke. Yet the dark matter, unaffected by the crash, sailed straight through, revealed only by how its gravity bent the light of distant galaxies. This cosmic car wreck became one of the strongest proofs that dark matter exists, and that it behaves unlike anything we've ever touched. Galaxy clusters are also cosmic scales. By measuring how they warp space-time, astronomers can weigh the universe itself. Einstein predicted that massive objects would bend light, and clusters do exactly that, acting as gravitational lenses that magnify and distort galaxies behind them. Sometimes they twist background galaxies into glowing arcs. Einstein's rings a celestial funhouse mirror that lets us peer even deeper into space. And when we tally up the mass of all the gas, galaxies, and dark matter in a cluster, we get a number that hints at the universe's total composition. How much is matter, how much is dark energy, and how much is still unaccounted for. Yet for all their grandeur, these clusters are more than just cosmic curiosities. They're snapshots of how the universe builds complexity. Every galaxy within them carries a history. Some are ancient relics, others vibrant with newborn stars, and a few even show signs of cannibalizing their neighbors. The hot gas between them tells tales of supernova explosions and black hole eruptions, while the dark matter's distribution whispers secrets about the universe's infancy. Together, they form a living archive, a record of how gravity sculpts order from chaos over billions of years. So the next time you gaze at a cluster's shimmering glow, remember, you're not just seeing a collection of galaxies. You're witnessing the universe's most ambitious construction project, a testament to the forces that shape everything from the tiniest atom to the vast cosmic web. The Milky Way isn't just drifting through space, it's riding a current, part of a vast celestial river flowing toward an unseen destination. Welcome to Laniakea, our home supercluster, a 500 million light-year-wide tapestry of galaxies all moving in unison, like a school of fish swept along by the same cosmic tide. The name Laniakea means immeasurable heaven in Hawaiian, and it couldn't be more fitting. This structure isn't just a random grouping, it's a gravitational watershed, with every galaxy inside it, including ours, drawn inexorably toward the Great Attractor, as if pulled by some invisible undertow. Mapping Laniakea was like uncovering a continent hidden beneath fog. Astronomers didn't use telescopes to trace its edges. They tracked the subtle motions of galaxies, the way leaves floating on a stream reveal the water's flow. By measuring how thousands of galaxies drift through space, they noticed something extraordinary. Entire clusters were moving together, not randomly, but in a coordinated dance toward a single point. These galactic currents outlined Laniakea's feathery shape, with filaments stretching outward like branches of a celestial tree, each one studded with galaxy clusters glowing like dew on a spider's web. What's astonishing is how small we are within it. Laniakea contains roughly 100,000 galaxies, yet it's just one thread in the cosmic web's grand design. At its heart lies the Norma cluster, a dense knot of galaxies acting as the supercluster's gravitational anchor. But even this immense structure isn't the end of the story. Laniakea itself is likely part of something even larger, perhaps connected to neighboring superclusters like Shapley or Perseus Pisces in ways we're only beginning to grasp. This discovery rewrote our cosmic address. For centuries, we thought of Earth as the center of everything, then our solar system, then the Milky Way. Now we know our galaxy is just one speck in a supercluster among countless others, each with its own flow, its own destiny. And just as rivers on Earth merge into ever larger waterways, superclusters may be tributaries to something vaster, a structure so immense we can't yet see its shape. Could there be a meta-supercluster linking Laniakea to others? Does the cosmic web have hierarchies we've yet to uncover? What's clear is that Laniakea teaches us a humbling lesson. The universe organizes itself on scales we're only starting to comprehend. Every galaxy within it, from the brightest spiral to the faintest dwarf, is part of a shared journey, one that began with the Big Bang and will continue long after our own star has faded. And as we map more of these galactic currents, we're not just charting space, we're learning how gravity writes its story across billions of years, one swirling eddy at a time. Imagine measuring the same room with two rulers and getting wildly different results. That's the puzzle astronomers face with the Hubble tension. At the heart of this cosmic rift lies a simple question: how fast is the universe expanding? When Edwin Hubble first discovered galaxies racing away from us, he unlocked a fundamental truth: space itself is stretching. But today, that truth has fractured into two conflicting measurements, each backed by impeccable evidence, yet refusing to agree. One method uses the cosmic microwave background, the afterglow of the Big Bang, to calculate the expansion rate from the infant universe. Another relies on nearby stars and supernova, whose brightness acts like mile markers in space. The problem: these approaches disagree by about 9%, a gap that sounds small but shakes the foundation of cosmology. If the cosmic web's expansion isn't uniform, what does that mean for dark energy, the mysterious force driving it? Could dark energy be changing over time, growing stronger or weaker in ways we haven't accounted for? Or is there something flawed in our models, an overlooked ingredient in the universe's recipe? The cosmic web structure adds another layer of intrigue. Baryon acoustic oscillations, those frozen sound waves from the early universe, suggest one expansion rate when measured in galaxy distributions. Yet supernova in those same galaxies tell a different story. It's as if the universe is whispering two secrets at once, forcing us to question which one, if either, is true. Some theorists propose exotic fixes. Maybe dark matter interacts in unexpected ways, or gravity behaves differently on cosmic scales. Others wonder if we're seeing evidence of parallel universes nudging our own. What's undeniable is that the Hubble tension isn't just a technical glitch, it's a beacon pointing toward undiscovered physics. Every conflicting measurement is a clue, a hint that the cosmic web's grand design might be more complex than we imagined. And as telescopes grow sharper and simulations more precise, we're not just solving a puzzle. We're rewriting the story of how the universe unfolds, one contradictory data point at a time. The cosmic microwave background is more than just ancient light. It's the universe's first photograph, a baby picture taken when everything was just 380,000 years old. But this snapshot isn't smooth. Zoom in and you'll find a patchwork of faint temperature variations, some spots slightly warmer, others cooler, like the brushstrokes of a cosmic artist. These tiny fluctuations, no more than 1 part in 100,000, are the seeds from which the entire cosmic web grew. The warmer patches, those became the dense hubs of galaxy clusters. The cooler spots, they stretched into the vast, empty voids we see today. It's staggering to think that the grand design of everything, from the Milky Way to the farthest quasar, traces back to these whispers of uneven heat in the newborn cosmos. The Planck satellite, launched by the European Space Agency, spent years mapping these variations with breathtaking precision. Its all-sky images reveal a mottled pattern, a fingerprint of the universe's raw potential. What's astonishing is how well these ancient fluctuations match the cosmic web we observe now. The same mathematical patterns appear in both, like comparing a sculptor's sketch to the finished statue. Planck's data showed that the distribution of hot and cold spots isn't random. They follow a specific rhythm, a signature of quantum fluctuations stretched to cosmic scales by inflation, the universe's explosive initial growth spurt. Here's where it gets even wilder. Those quantum fluctuations were microscopic, smaller than an atom when they first emerged, but inflation, that trillionth of a second expansion, blew them up to astronomical sizes. Imagine blowing up a single grain of sand to the scale of a galaxy cluster. That's the level of magnification we're talking about. and as gravity went to work over billions of years, it amplified these tiny differences, sculpting them into the filaments, clusters, and voids we recognize today. The cosmic web isn't just shaped by these initial conditions, it's a direct descendant of them. But the CMB isn't just a relic, it's a Rosetta Stone for decoding the universe's composition. By analyzing the size and distribution of these temperature variations, scientists can calculate the exact mix of ordinary matter, and dark energy that makes up the cosmos. The patterns tell us that dark matter must be cold and slow-moving, or the web structure wouldn't match so perfectly. They also hint at dark energy's presence, subtly influencing how clusters and voids formed over time. It's like reconstructing a recipe from the crumbs left on a plate, except the plate is the entire observable universe. What's truly humbling is that this light has traveled for over 13 billion years to reach us. The photons hitting Planck's detectors began their journey before Earth existed, before the Milky Way took shape, even before the first stars flickered to life. And they carry a message from the universe's infancy, a blueprint that's still unfolding. Every galaxy, every filament, every void is part of a story written in those primordial temperature variations, a story we're only just beginning to read. So when you look at a map of the cosmic web, remember, you're not just seeing where things are, you're seeing how they began. We think we know what the universe is made of until we count it up and realize half is missing. Not dark matter or some exotic substance, but ordinary atoms, the same protons and neutrons that build stars, planets, and even our bodies. Scientists call this the missing baryon problem, and it's one of cosmology's most perplexing accounting errors. Based on the cosmic microwave background, we can calculate exactly how much normal matter should exist. Yet when we tally up all the visible stars, galaxies, and gas clouds, nearly 50% of it simply vanishes. Where did it go? The answer lies in the cosmic web's faintest threads, where matter is so sparse it's practically invisible until now. The culprit is something called the warm-hot intergalactic medium, or WIM. Picture this, the cosmic web isn't just galaxies and voids. It's also a labyrinth of ultra-thin gas filaments, so diffuse they'd make Earth's best vacuum chambers seem crowded. This gas isn't cold or dense enough to glow like a nebula, nor is it hot enough to shine brightly in X-rays. Instead, it lingers in a ghostly middle ground, warm to temperatures between 100,000 and 10 million degrees by shocks from galaxy collisions and supernova explosions. Detecting it is like trying to spot a single lit match in a foggy stadium, but astronomers have devised ingenious ways to catch its faint signature. One method relies on distant quasars, the brilliant cores of active galaxies whose light pierces through the cosmic web like a flashlight beam. As this light travels toward us, the WIM-sparse gas absorbs specific wavelengths, leaving tiny dips in the quasar spectrum, like a barcode of missing colors. The Chandra and XMM Newton telescopes have spotted these fingerprints in X-rays, revealing oxygen and nitrogen atoms ionized by the WIM heat. Another clue comes from the Sunyaev-Zeldovich effect, where the cosmic microwave background's photons get a slight energy boost when they scatter off electrons in these filaments. It's as if the universe left us breadcrumbs in the form of distorted microwaves and stolen starlight. Why does this matter? Because these hidden baryons aren't just idle spectators, they're the cosmic web's lifeblood. Over billions of years, gravity slowly funnels this gas along filaments toward galaxies, fueling new star formation like rivers feeding a forest. Without it, galaxies would starve, their growth stunted long ago. The WIM also holds clues to how the universe redistributes its matter, acting as a reservoir for elements forged in supernova and black hole winds. Every atom in your body likely passed through these invisible currents before settling into a star, then a planet, and eventually you. solving the missing baryon problem isn't just about balancing the universe's books. It's proof that the cosmic web's grand design includes even its faintest brushstrokes. As telescopes grow more sensitive, we're finally seeing the full picture. Not just the glittering cities of galaxies, but the quiet highways connecting them, where the universe's ordinary yet elusive matter has been hiding all along. The cosmic web isn't just shaped by gravity. It might also be threaded with invisible magnetic highways stretching between galaxies like cosmic power lines. These aren't the familiar magnetic fields of planets or stars. These are vast, diffuse structures, possibly as old as the universe itself, woven into the fabric of filaments that connect galaxy clusters. Imagine a spider's web glistening with dew, but instead of water droplets, it's strung with forces strong enough to bend the paths of high-energy cosmic rays. The origins of these magnetic fields are still a mystery. Some theories suggest they were born in the chaos of the Big Bang, frozen into space as the universe expanded. Others argue they were forged later, sculpted by the winds of exploding stars or the jets of supermassive black holes, which could have pumped energy into the cosmic web like invisible bellows. Detecting these fields is like trying to hear a whisper in a hurricane. They're too faint to see directly, but their presence leaves subtle clues. When cosmic rays particles racing across space at nearly the speed of light pass through magnetized filaments, their paths curve ever so slightly. Radio telescopes like LOFAR, with its sprawling network of antennas across Europe, are tuned to catch the faint radio glow emitted by these twisted particles. It's painstaking work, like reconstructing a symphony from the echoes of a single note. But early observations hint that these fields might be real, their tendrils aligning with the cosmic web's filaments in ways that defy coincidence. What's even more intriguing is how these magnetic fields might shape the universe's evolution. They could act as cosmic traffic cops, steering charged particles toward galaxies and influencing where stars are born. In dense filament regions, magnetic pressure might slow down gas collapse, putting the brakes on star formation. Elsewhere, they could funnel material into galaxies, feeding their growth. And if these fields are truly primordial, they'd be a fossil record of the universe's infancy, a relic of forces that shaped reality before the first stars flickered to life. Yet the puzzle deepens when we consider scale. Magnetic fields are usually tied to objects: a star, a planet, a galaxy, but these filaments are different. They're not bound to anything. They're the space between the spaces, the scaffolding itself. How do magnetic fields persist across such vast, empty reaches? Some researchers speculate that turbulence in the cosmic web's sparse gas could amplify weak fields over time, like a dynamo spinning in slow motion. Others wonder if dark matter plays a role, its invisible interactions somehow sustaining these forces. Every new observation peels back another layer of the mystery. Recent studies of galaxy clusters reveal that their magnetic fields might be connected, as if the web is laced with a continuous magnetic mesh. And if that's true, it changes how we think about the universe's structure. The cosmic web isn't just a map of matter. It's a living, dynamic system crackling with invisible energy. As telescopes grow more sensitive, we're not just mapping galaxies and voids anymore. We're tracing the unseen forces that stitch them together, uncovering a universe far more intricate than we ever imagined. At the heart of nearly every galaxy, including our own Milky Way, lurks a monster, a supermassive black hole, weighing millions or even billions of times more than our Sun. These aren't just cosmic vacuum cleaners, silently devouring everything that strays too close. They're dynamic engines, shaping their galaxies and the wider cosmic web in ways we're only beginning to understand. Picture a black hole not as a passive drain, but as a sculptor, carving vast cavities in the intergalactic gas with jets of energy so powerful they can stretch for millions of light years. These jets, traveling at nearly the speed of light, heat the surrounding gas to millions of degrees, preventing it from cooling and collapsing into new stars. It's a cosmic thermostat regulating galaxy growth with precision. Take the galaxy M87, home to one of the most famous black holes ever imaged. Its jet, a blazing spike of plasma, stretches 5,000 light-years into space, pumping energy into the surrounding cluster like a celestial blowtorch. Similar jets have been spotted across the universe, often aligned with the cosmic web's filaments, as if black holes are stitching their influence into the universe's very fabric. Without this feedback, galaxies would grow unchecked, gorging on gas until they became bloated giants, distorting the web's delicate equilibrium. Instead, black holes act as cosmic stabilizers, their outbursts creating vast bubbles in the intergalactic medium, regions where star formation is suppressed and the web's structure is subtly rewritten. But here's the twist: black holes aren't just destroyers. Their explosive deaths might also be creators. When two galaxies collide, their central black holes spiral together, eventually merging in a cataclysm that sends gravitational waves rippling through space-time. These collisions can kick the newly formed black hole out of its galaxy at incredible speeds, sending it careening through the cosmic web like a rogue bullet. Along the way, it drags stars, gas, and even dark matter with it, potentially seeding new structures in its wake. Some theories suggest these wandering black holes could even trigger star formation in their paths, like celestial plows tilling the interstellar medium. The relationship between black holes and the cosmic web is a dance of chaos and order. Their jets can carve voids, their mergers can redistribute matter, and their gravity can anchor entire galaxies. Yet for all their power, they're also bound by the web they help shape, their fates intertwined with the filaments and clusters they inhabit. It's a reminder that the universe's largest structures are built not just by gravity's gentle pull, but by the violent, brilliant outbursts of its most enigmatic inhabitants. And as we peer deeper into the cosmos, we're finding that black holes aren't just features of the cosmic web. They're its architects, its regulators, and perhaps even its storytellers. The universe loves patterns that repeat, not just in the delicate spirals of seashells or the branching veins of leaves, but across the vast expanses of the cosmic web. Zoom in on a galaxy cluster and you'll see filaments branching into smaller filaments, galaxies huddled in knots like tiny reflections of the grand design. Pull back and those same clusters become mere dots along threads of an even larger tapestry. This self-similarity, this echo of structure at every scale, is the hallmark of fractals' mathematical shapes where the whole mirrors its parts, no matter how deeply you look. And the cosmic web might be the ultimate fractal, a universe-sized example of nature's obsession with repeating blueprints. Gravity is the artist behind this infinite recursion. Just as it sculpts galaxies into spirals and clusters into dense knots, it carves the same patterns whether it's acting on a cloud of gas light years across or the entire observable universe. The reason gravity doesn't care about scale. Its equations work the same way whether you're calculating the orbit of a moon or the collapse of a galactic supercluster. That's why filaments at every level, from the tendrils connecting dwarf galaxies to the massive bridges between superclusters, share the same twisted, thread-like shape. It's as if the universe took a single brushstroke and replicated it across every possible dimension. But here's where it gets eerie. Some researchers argue this fractal behavior goes beyond gravity. The distribution of matter in the cosmic web matches mathematical models used to describe everything from earthquake tremors to stock market fluctuations, systems where complexity emerges from simple rules. Could the universe's structure be the result of similar underlying principles? One provocative theory suggests that quantum fluctuations in the early universe, stretched to cosmic scales by inflation, imprinted this fractal order like a watermark on reality itself. If true, it means the universe didn't just evolve into this pattern, it was born with it, a cosmic fingerprint woven into space-time, yet mysteries remain. While the cosmic web is fractal-like, it isn't perfectly so. At extremely large scales, the pattern smooths out, as if the universe finally runs out of patience for repetition. This transition point where the fractal illusion breaks could hold clues to dark energy's influence or reveal where our understanding of physics hits its limits. Meanwhile, supercomputer simulations like Illustris show that even in virtual universes governed solely by gravity and known physics, these fractal patterns emerge spontaneously. That's the beauty of this pattern. It's both a reflection of nature's simplicity and a reminder of how much we still have to learn. What's truly humbling is that this fractal design isn't just a cosmic curiosity. It's a bridge between the infinitely large and the infinitesimally small. The same spirals we see in galaxies appear in hurricanes and swirling coffee cream. The branching of cosmic filaments mirrors the growth of neurons in our brains. It's as if the universe, for all its complexity, keeps returning to a handful of elegant designs, each iteration telling us something new about the hidden order beneath the chaos. And as we map more of the cosmic web's fractal twists, we're not just charting galaxies, we're decoding the universe's favorite shape. The cosmic web didn't just form by chance, it's a living structure, constantly evolving under the push and pull of forces we're only beginning to understand. But what happens when dark energy, that mysterious force accelerating the universe's expansion, tightens its grip? Simulations paint a startling picture. Filaments stretched thin, galaxies ripped from their clusters, and vast regions of space left eerily empty. Within 100 billion years, the universe could become a place where distant galaxies vanish from view entirely, their light stretched beyond detectability as space itself expands faster than light can traverse it. The cosmic web, once a vibrant network, might fracture into isolated islands of matter, each drifting alone in an ever-cooling void. Yet this bleak scenario isn't the only possibility. Some models suggest that gravity could rally in certain regions, forming localized webs where clusters like Laniakea remain bound together even as the rest of the universe tears apart. Picture a shipwrecked crew clinging to floating debris in an endless ocean, except here, the debris is entire superclusters, and the ocean is an unimaginably vast, darkening cosmos. Within these surviving pockets, galaxies might continue to collide, merge, and even birth new stars long after the rest of the universe has faded to black. It's a haunting thought. Civilizations born in that far future would gaze into their skies and see only their own cluster, with no hint of the cosmic web's once grand design. The irony is that dark energy, the same force dooming the web's large-scale structure, could also reshape it in unexpected ways. As expansion accelerates, the spaces between filaments widen, but gravity within dense regions grows more concentrated. This might trigger new forms of clustering, like cosmic cul-de-sacs where matter collapses into hyper-dense knots. Some theorists even speculate about relic structures, frozen echoes of the web's glory days, preserved like insects in amber as the universe races toward heat death. What's undeniable is that the cosmic web's fate is tied to the universe's deepest mysteries. Is dark energy constant, or could it change over time? If it weakens, gravity might regain the upper hand, allowing the web to persist in some form. If it strengthens, the universe's expansion could eventually shred atoms themselves. A hypothetical Big Rip scenario where not even stars or planets survive. Every observation of distant galaxies, every measurement of the universe's expansion, brings us closer to answering these questions. For now, we're left with simulations and speculation, tracing faint clues in the light of galaxies billions of years gone. But this much is clear: the cosmic web story doesn't end with its dissolution. It's a reminder that the universe is never static. It's a dynamic, ever-changing arena where even the largest structures are fleeting. And as we peer into the future, we're not just predicting the web's demise, we're glimpsing the ultimate fate of everything. Is Earth's existence just a cosmic roll of the dice, or could the universe's largest structures have subtly tilted the odds in our favor? The cosmic web's sprawling architecture might do more than arrange galaxies. It could shape the very conditions for life itself. Picture two regions, a dense galaxy cluster, where stars are packed so tightly that supernovae explode like fireworks, bathing nearby planets in lethal radiation. Now shift your gaze to a quieter filament, where galaxies drift at safer distances, their planets bathed in gentler starlight. The difference isn't just scenery, it's a matter of survival. In the cluster, life might be snuffed out before it even begins. Along the filaments, worlds could enjoy the stability needed for evolution to work its slow magic. This isn't just speculation, it's a numbers game. In crowded clusters, the rate of catastrophic stellar explosions could be hundreds of times higher than in sparser regions. A planet in the wrong neighborhood might face extinction-level events every few million years, resetting the clock on complex life. But in the cosmic web's quieter suburbs, where galaxies are spaced just right, planets could enjoy billions of years of uninterrupted calm. Our own Milky Way sits in a Goldilocks zone, not too isolated, not too crowded, nestled in a filament of Laniakea with enough stellar neighbors to enrich space with heavy elements, yet distant enough to avoid constant sterilization. The web's influence might extend even deeper. Filaments funnel gas between galaxies, seeding them with the raw materials for stars and planets. A galaxy positioned along a rich filament might receive a steady supply of hydrogen, ensuring generations of star birth and the carbon, oxygen, and iron essential for life. Meanwhile, galaxies stranded in voids could starve, their star formation stunted by lack of fuel. It's a cosmic buffet, and where a galaxy sits determines whether it feasts or famishes. But here's the provocative twist: the web could also dictate the timing of life's emergence. In the early universe, filaments were more chaotic, their galaxies colliding frequently, triggering bursts of star formation and radiation. Only as the web matured, its structure stabilizing over billions of years, did quiet, life-friendly pockets emerge. That suggests a chilling possibility. We might be among the first intelligent civilizations, simply because the universe needed time to build safe neighborhoods. Or conversely, we could be latecomers, arriving after countless others rose and fell in denser, more dangerous regions. The ultimate question isn't just whether life exists elsewhere, but whether the cosmic web's architecture makes it inevitable or vanishingly rare. If the universe's grand design favors life in certain crannies, then Earth's position isn't random. It's a testament to the delicate balance of forces that shaped not just galaxies, but the fragile conditions for consciousness itself. And as we search for other life, we're not just scanning stars, we're reading the hidden map of a universe that might have been built, stitch by stitch, with life in mind. What if our cosmic web isn't the only one? Beyond the edges of our observable universe, beyond even the farthest galaxies racing away from us, there might be other webs entirely, vast, intricate structures woven by different laws of physics, each one a universe unto itself. This isn't science fiction. It's a serious possibility grounded in theories like inflationary cosmology and string theory. Imagine a multiverse where gravity is stronger, pulling galaxies into tighter knots, or where dark energy is weaker, allowing webs to grow denser and more tangled. Some universes might lack dark matter entirely, their filaments sparse and fragile. Others could be so dense with matter that their cosmic webs resemble shimmering lace, galaxies packed edge to edge in a dizzying embrace. The idea emerges from the math behind cosmic inflation, the theory that our universe underwent a rapid expansion in its earliest moments. If inflation can happen once, why not countless times, birthing bubble universes with their own unique physics? String theory takes it further, suggesting higher dimensional brains could collide, sparking new universes like soap bubbles merging in a sink. In these scenarios, the cosmic web isn't just a feature of our universe, it's a fingerprint, a telltale sign of the fundamental forces that shaped it. And if other webs exist, their structures would carry their own stories, written in the language of alternate physics. Evidence is elusive, but not impossible to imagine. If a neighboring universe brushed against ours long ago, the collision might have left a faint imprint in the cosmic microwave background, a strange, circular bruise in the afterglow of the Big Bang. Some researchers have scoured Planck satellite data for these anomalies, though none have been confirmed. Others propose that dark energy's mysterious strength in our universe could be a clue, a fluke of random chance in a multiverse where every possible value exists somewhere. The implications are staggering. If the multiverse is real, then our cosmic web's delicate balance, the precise strength of gravity, the exact amount of dark energy, might not be fine-tuned for life at all. It could just be one roll of the dice in an endless casino of universes, most of them sterile and inhospitable. Or perhaps life thrives in forms we can't fathom, adapted to webs woven by alien physics. Either way, the cosmic web becomes more than a structure. It's a message in a bottle, hinting at realities beyond our own. For now, the multiverse remains a breathtaking hypothesis, a shadow on the edge of science. But every time we map another filament, measure another galaxy's motion, or decode another ripple in the CMB, we're not just studying our universe, we're asking whether it's the only one, and whether the cosmic web's patterns are unique, or just one thread in an infinite tapestry. Something is pulling on our cosmic web, not just gently, but with enough force to send thousands of galaxy clusters streaming in the same direction, like leaves caught in a phantom wind. Astronomers call this eerie motion dark flow, and it's one of the most baffling patterns in the universe. These aren't random drifts. Entire superclusters are moving with eerie coordination toward a single point beyond the edge of our observable universe, as if tugged by something massive lurking in the shadows. The strangest part, there's nothing visible there, no known galaxy, no supercluster, nothing that should exert such a pull. Yet the evidence is written in the distorted paths of galaxy clusters, their motions betraying the presence of something we can't see. The first clues emerged from studies of the cosmic microwave background, the afterglow of the Big Bang. Subtle distortions in this ancient light revealed that galaxy clusters aren't just drifting apart with the universe's expansion, they're also being dragged en masse toward a mysterious attractor. Some measurements suggest this flow stretches over billions of light years, carrying clusters at speeds exceeding 1,000 kilometers per second. That's like spotting every river on Earth suddenly bending toward a hidden ocean beyond the horizon. Theories about what's causing this are as dramatic as the phenomenon itself. One possibility is an unimaginably vast superstructure, a concentration of mass so colossal it warps the cosmic web from beyond our observational limits. Picture a mountain range so huge, its foothills lie outside our field of view, yet its gravity still pulls us toward its slopes. Another idea dips into exotic physics. Perhaps dark flow is evidence of a neighboring universe brushing against ours, its gravity leaking through the fabric of space-time. Or maybe it's a sign that our patch of the cosmos isn't as uniform as we thought, that inflation didn't smooth everything out, leaving behind wrinkles of density powerful enough to steer galaxies like cosmic rivers. Not everyone is convinced. Skeptics argue these motions could be statistical flukes or artifacts of incomplete data. After all, measuring bulk flows is like trying to track a school of fish in a stormy ocean. The currents are subtle, the noise overwhelming. Yet newer surveys, like those from the E-Rosetta X-ray telescope, continue to find anomalous cluster motions that align eerily with earlier dark flow claims. The debate rages because the stakes are cosmic. If dark flow is real, it means our universe's structure extends far beyond what we can observe, shaped by forces or realms we've yet to discover. What's undeniable is how this mystery exposes the limits of our cosmic maps. We're used to thinking of the observable universe as our entire playing field, but dark flow hints at a bigger game, one where the cosmic web might be just one thread in a tapestry too vast to fathom. Whether it's hidden mass, alternate physics, or something even stranger, this enigmatic motion reminds us that the universe's grand design is still being written. And somewhere beyond the edge of our vision, invisible hands may still be shaping it. Long before galaxies filled the cosmos, the universe was a shadowy realm of floating hydrogen, a ghostly blueprint waiting for its first spark. This was the cosmic web in its infancy, an invisible scaffold of gas stretching through the darkness, so diffuse you could fly through a light year of it and barely graze a single atom. Then, around 200 million years after the Big Bang, something extraordinary happened. Deep within those filaments, pockets of hydrogen began collapsing under their own gravity, heating up until nuclear fires ignited, the first stars in existence. Their birth didn't just light up the darkness, it set the entire universe ablaze with transformation, an era astronomers call the Epoch of reionization. These pioneer stars were nothing like the Sun. Hundreds of times more massive, they burned furiously and died young, their ultraviolet radiation shredding nearby hydrogen atoms into ions. Gradually, this ionization spread like wildfire, clearing the cosmic fog and making the universe transparent for the first time. Picture a frozen lake at dawn, its icy surface cracking into countless glittering shards as sunlight breaks through, except here, the lake is the cosmos itself, and the light is the birth cry of creation. Now, the James Webb Space Telescope is our time machine to this primordial dawn. Peering deeper into infrared than any instrument before it, JWST has spotted galaxies from this epoch so distant their light has traveled over 13 billion years to reach us. And what's astonishing isn't just their age, it's how they're arranged. These infant galaxies aren't scattered randomly. They're strung along the cosmic web's filaments like dew on a spider's silk, proving the web's structure guided the universe's first lights. Some galaxies appear brighter than expected, their starlight magnified by the gravitational lensing of dark matter, another clue that the web's hidden scaffolding was already shaping everything. Yet mysteries linger. Why did reionization happen in patches rather than uniformly? How did those first stars influence the web's later evolution? Simulations suggest their explosive death seeded space with heavy elements, enriching future generations of stars. Meanwhile, their radiation might have pushed gas out of small galaxies, starving them of fuel and stunting their growth. It's a cosmic feedback loop. The web birthed the stars, and the stars, in turn, rewrote the web. This epoch wasn't just a phase, it was the universe's adolescence, a turbulent transition from simplicity to complexity. And as JWST unveils more of these ancient galaxies, we're not just observing the past, we're watching the cosmic web awaken, one brilliant spark at a time. Our simulations of the cosmic web paint a universe teeming with tiny galaxies, swarms of dwarf satellites that should orbit large galaxies like the Milky Way. But when astronomers peer into our cosmic neighborhood, they find a puzzling emptiness. Where are all these missing satellites? This discrepancy isn't just a minor accounting error. It's a gaping hole in our understanding of how galaxies form within the web's intricate framework. The math says there should be hundreds of these small, faint galaxies dancing around us, yet we've only spotted a few dozen. Either something's wrong with our models, or the universe is playing by rules we haven't cracked yet. One leading theory points to the cosmic web's ruthless physics. Filaments and voids aren't just passive backdrops, they're dynamic arenas where gravity's tidal forces can stretch and shred smaller galaxies over time. Picture a fragile raft caught in a swirling river, slowly pulled apart by unseen currents. Dwarf galaxies with their weak gravitational grip might face a similar fate. As they drift through the web's filaments, tidal forces could strip away their stars and gas, leaving behind only faint trails of debris, cosmic ghosts too dim for our telescopes to spot. But here's where dark matter complicates the mystery. Most simulations assume dark matter behaves predictably, clumping into halos that cradle galaxies. If these halos are as abundant as models suggest, they should protect dwarf galaxies from total destruction. Yet the dwarfs we do observe often look oddly pristine, their stars clustered tightly, as if they've never been disrupted. This has led some scientists to propose a radical idea. Maybe dark matter isn't as placid as we thought. Alternative theories suggest dark matter might be warm, meaning its particles move fast enough to smooth out small-scale clumps, effectively erasing the smallest galaxies before they can fully form. The debate gets even thornier when we look at the Milky Way's surviving dwarfs. Many orbit in a thin plane, like coins scattered on a table, rather than the random swarm simulations predict. This unexpected alignment hints that the cosmic web's filaments might be herding them into position, or that our galaxy's history of collisions has left an imprint we're only beginning to decipher. Every missing satellite is a clue, a silent witness to forces we're still learning to measure. New telescopes like the Vera Rubin Observatory could finally spot these elusive dwarfs, revealing whether they're hiding in plain sight or truly absent. Until then, the mystery stands as a humbling reminder. Even in our own galactic backyard, the cosmic web's grand design holds secrets we've yet to unravel. The cosmic web's grand design might trace back to the tiniest vibrations in existence, quantum fluctuations so small they defy comprehension. Picture the universe in its first fleeting moments, a seething ocean of energy where particles flickered in and out of existence, their brief lives governed by quantum uncertainty. These microscopic ripples, no larger than a billionth of a proton, should have faded into oblivion. Instead, something extraordinary happened. Inflation, the universe's exponential growth spurt, stretched these quantum tremors across cosmic scales, magnifying them into the seeds of galaxies, filaments, and voids. What was once a whisper in the quantum foam became the blueprint for everything we see today. This quantum-to-cosmic connection is one of the most profound ideas in modern physics. It means the cosmic web's sprawling filaments aren't just accidents of gravity. They are fossilized imprints of the universe's quantum infancy. Imagine blowing up a snowflake to the size of a continent. Its intricate symmetry would mirror the original, just as the web's structure echoes those primordial quantum jitters. The evidence is etched into the cosmic microwave background, where temperature variations match predictions of quantum fluctuations stretched by inflation. It's as if the universe took a snapshot of its own quantum roots and left it glowing in the sky for us to decode. But how does something so small shape something so vast? The answer lies in inflation's explosive power. In less than a trillionth of a second, the universe expanded faster than light itself, amplifying those quantum ripples into density variations, slightly denser patches where matter would later cluster, and thinner regions destined to become voids. Gravity then spent billions of years sculpting these variations into the web we observe, turning quantum noise into cosmic architecture, the eerie part. Without these fluctuations, the universe might have remained perfectly smooth, a featureless expanse devoid of stars, galaxies, or life. This idea bridges two seemingly unrelated worlds, particle physics and cosmology. The same quantum mechanics that governs electrons and quarks also dictated the universe's large-scale structure. Some theories even suggest that dark matter, the web's invisible scaffold, might consist of particles born from those early quantum fields. If true, it would mean the cosmic web isn't just shaped by quantum history, it's still woven from it, with dark matter threads humming to the same ancient tune. Yet mysteries linger. Why did inflation amplify certain fluctuations and not others? Could there be deeper quantum signatures hidden in the web's patterns, waiting to reveal new physics? Experiments like the upcoming LightBird satellite aim to measure the CMB with unprecedented precision, hunting for clues in the polarization of ancient light. Meanwhile, quantum gravity theories speculate that space-time itself might have a granular, pixelated texture at the smallest scales, a relic of the quantum realm that could subtly warp the web's formation. What's certain is that the cosmic web isn't just a structure, it's a time capsule, preserving the universe's quantum origins in filaments of galaxies and light. Every time we map its tendrils, we're not just charting space, we're reading the first lines of creation's story, written in the language of the infinitesimal and stretched across the cosmos. Early in the universe's history, everything was perfectly symmetrical, a hot, dense soup where matter and energy were distributed almost uniformly, like steam rising from a boiling pot. Yet today, we see a cosmos fractured into filaments and voids, a lopsided tapestry where matter clusters in some regions and vanishes from others. This dramatic shift from symmetry to asymmetry is one of the cosmic web's deepest mysteries, and the key lies in a process called symmetry breaking. Think of it like water freezing into ice. At high temperatures, water molecules move chaotically, appearing identical in every direction. But as it cools, invisible forces guide the molecules into rigid, crystalline patterns. Suddenly, the symmetry shatters and structure emerges where there was none. The universe underwent a similar transformation as it expanded and cooled. Tiny quantum fluctuations, magnified by inflation, created regions where matter was ever so slightly denser. Gravity seized these imperfections, amplifying them over billions of years until the smooth primordial soup fractured into the cosmic web's intricate filaments and voids. Without this breaking of symmetry, the universe might have remained a featureless haze, devoid of galaxies, stars, or planets. Instead, those initial imperfections became the seeds of everything we see today. What's fascinating is how this mirrors phase transitions in everyday life. A magnet heated to extreme temperatures loses its polarity, its atoms jostling too violently to align. But as it cools, its atoms suddenly snap into orderly rows, creating a north and south pole where none existed before. The cosmic web structure emerged through a similar cosmic cooling, not of temperature but of energy. As the universe expanded, the forces governing matter like electromagnetism and the strong nuclear force decoupled, each carving its own domain in space. This triggered cascading instabilities, regions where matter could no longer stay evenly spread. But why filaments and voids? Why not clumps or sheets? The answer lies in dark matter's ghostly influence. Simulations show that cold dark matter, slow-moving and weakly interacting, naturally collapses into elongated tendrils under gravity's pull, leaving vast empty regions between them. Ordinary matter then flows along these dark matter highways, pooling at intersections to form galaxies. It's a cosmic sorting mechanism, with gravity acting as the sieve that separates the dense from the desolate. This pattern isn't just a curiosity, it's a window into physics at the universe's most fundamental level. The same symmetry-breaking processes that shaped the cosmic web might govern phenomena from the behavior of subatomic particles to the evolution of life itself. After all, asymmetry is what makes complexity possible. Without it, there would be no variation, no structure, no stars, no planets. The cosmic web's lopsided beauty is a testament to the power of imperfection, a reminder that even the universe's grandest designs begin with the smallest breaks in symmetry. For thousands of years, humans have gazed at the night sky and seen more than random stars. They've seen stories. The ancient Greeks traced heroes and beasts in the constellations. The Maya mapped celestial cycles to guide their cities, and Polynesian navigators read the heavens like a roadmap across the Pacific. These patterns weren't just myths, they were humanity's first attempts to impose order on the cosmos, to transform the unknown into something familiar. Today, we're still mapping the sky, but instead of connecting stars into shapes, we're tracing the cosmic web's filaments, using supercomputers instead of storytelling. The tools have changed, but the impulse remains the same: to find meaning in the chaos, to uncover the hidden rhythms of the universe. What's remarkable is how this journey mirrors our own evolution, from seeing the cosmos as capricious gods to understanding it as a system governed by mathematics. Early skywatchers explained eclipses as dragons swallowing the sun. Now, we predict them down to the second using orbital mechanics. Where cultures once imagined the Milky Way as a river of souls, we now measure it as a spiral arm of the Laniakea supercluster. The cosmic web, with its precise gravitational choreography, is simply the latest chapter in humanity's never-ending quest to decode the heavens. Yet in some ways, it brings us full circle. Modern simulations of the web's filaments bear an uncanny resemblance to the world trees and celestial webs found in indigenous cosmologies, as if ancient intuition glimpsed shadows of a deeper truth. This convergence of myth and science reveals something profound about our place in the universe. The cosmic web isn't just an astronomical discovery, it's a mirror reflecting humanity's growing awareness of its own smallness and significance. We've gone from believing Earth was the center of creation to knowing we're a speck in an unfathomably vast network. Yet that network's very existence suggests an underlying order we can comprehend. That tension between awe and understanding is where science and philosophy meet. The web challenges us to hold both perspectives at once, to marvel at its beauty while dissecting its physics, to feel dwarfed by its scale while mapping its geometry. Perhaps that's the most human pattern of all. From cave paintings to quantum equations, we've always been creatures who search for connections between stars, between ideas, between each other. The cosmic web, in all its mathematical splendor, is more than a structure. It's a testament to the curiosity that drives us to keep looking up, keep questioning, keep weaving new stories from the darkness. And in that sense, every filament we chart isn't just a thread in the universe's design, it's part of our story too. From dark matter's invisible threads to the quantum ripples that seeded galaxies, the cosmic web's 22 patterns aren't just scientific curiosities. They're pieces of a puzzle we're only beginning to assemble. Every filament, every void, every inexplicable alignment whispers a story about forces we can't yet see and laws we don't yet understand. Think of it this way: for centuries we mapped coastlines without knowing the shape of continents. Now, with tools like the James Webb Space Telescope and next-generation dark matter detectors, we're finally charting the depths, discovering that the universe's blueprint is stranger and more intricate than anyone dreamed. What's exhilarating is how much remains hidden. The cosmic web isn't just a static relic, it's a living, evolving structure shaped by battles between dark energy's push and gravity's pull. Future observations might reveal filaments laced with magnetic fields we can't yet detect, or voids humming with energies that defy current physics. Some theories even suggest the web could hold traces of other universes' cosmic fingerprints left by collisions in dimensions beyond our own. Every answer we uncover seems to birth 10 new questions, and that's the thrill of exploration. But here's the most humbling part. This isn't just about distant galaxies. The same quantum fluctuations that sculpted the web also set the stage for stars, planets, and ultimately us. Those ancient ripples didn't just shape the cosmos, they made our existence possible. So when you look up at the night sky, remember, you're not just a spectator, you're a product of this grand design, a thread woven into the universe's story. Now it's your turn. Which pattern captivates you most? The Great Attractor's relentless pull, the fractal echoes in galaxy clusters, or the haunting silence of voids? Let's keep the conversation going. Drop your thoughts below. And if you're hungry for more cosmic mysteries, hit subscribe. The next chapter of discovery is already unfolding, and with your curiosity, we'll unravel it together. After all, the universe doesn't reveal its secrets to passive observers. It rewards those who dare to look